Welcome to the CFE Media and Technology Education Session, Best Practices for Designing and Specifying Motor and Drive Pairing. I'm your moderator, Mark T. Hosky with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to learn best practices for protecting motors and drives and understanding hazards, motor and drive sizing, motor and control methods, and specifying motors and drives for use with variable speed applications and more. Here is a list of learning objectives. We'll cover these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session agenda. If you'd like to take notes within the session, click on the left panel labeled Notes to do so. This session is available on demand if you need time to come back at any time. Please remember that this session will be made live at 10 a.m. Central, 11 a.m. Eastern, with a Q&A starting at approximately 10:45 a.m. Central and 11:45 a.m. Eastern, or immediately after the presentation ends if it runs a little bit longer than 45 minutes. Industry experts will answer viewer questions live, and those answers will be archived with the session. You can see the Q&A details in the Meetings tab on the left side of the screen. Here is some important information about obtaining an approved PDH for today's session. Today's speakers are Larry Leno, Senior Technical Specialist, Medium Voltage Adjustable Speed Drives, Motor and Drives Division, and Abel Cavazos, Senior Applications Engineer 2, Medium Voltage Motors, Motor and Drives Division, both with Toshiba International Corporation. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology. Next, a little more about each speaker. Larry Leno has more than 20 years experience with medium voltage drives, 17 of those years with Toshiba International Corporation. Larry has held many positions with Toshiba, including product instructor, training manager, service center manager, senior applications engineer, and section manager over distribution in the medium voltage drives department. This vast range of experience gives Larry the knowledge to apply adjustable speed drives to various applications. Larry has a degree in electronic engineering technology from the Ohio Institute of Technology. Abel Cavazos is a senior application specialist with a wealth of experience in providing motor solutions for highly specified applications. Abel works closely with application engineers of power systems and driven equipment to help develop the most efficient system possible. Larry and Abel, thanks for joining us. Please go ahead with your presentation.
Best practices for designing and specifying motor and drives pairing. Introduction. Specifying motors and drives for use with variable speed applications, environmental concerns, testings, things to watch out for. Additional application considerations for motors and drives, protecting motors and drives, conclusion and summary. Why should a motor and drive be specified together? Single point of responsibility ensures proper quoting to provide the right motor and drive for the application, installation and startup coordination. Also, some manufacturers will extend warranty with a motor and drive package. specifying motors and drives for use with variable speed applications.
So to specify motors and drives for use with variable speed applications, first let's talk about the motors. Motors are sized to meet a required torque. So the required torque is just how much it needs to drive a load and is a function of horsepower versus the speed. Okay. You also need to know the max torque, also known as breakdown torque and or overload capabilities. You also need to know the torque profile of the load. So whether it's going to be constant torque or variable torque. And then other typical motor application considerations that you need to know for the environment and whatever else. One key fact is typically motor service factor is 1.0 when it's matched to a variable frequency drive.
Variable speed drive sizing is done according to motor nameplate information. Number one, motor full load current, most important. Service factor, some companies like to run motors into service factor, so that is certainly a consideration. Motor speed and motor voltage. Motor current being the most important criteria, as VFDs are sized solely on motor current, taking into consider the application. There are two types of applications considered variable torque applications. Centrifugal fans, centrifugal pumps. In these types of loads, they require less torque at speeds less than 60 hertz. There's a lot of energy savings that can be had with these types of applications in running less than 60 hertz. As speed increases on these applications, as speed decreases in these applications, torque decreases with the square of the speed, and the motor horsepower decreases with the cube of the speed. Constant torque applications include ball mill, sag mill, conveyor, compressor, shredders, crushers. In constant torque applications, torque is not a function of speed. As speed changes, torque load remains the same. Horsepower changes linearly with change in speed. Constant horsepower loads include grinder, winding machines, and lathes. When it comes to constant horsepower loads, torque is a function of speed. As the speed of the operation is decreased, torque is increased, keeping horsepower constant. Constant horsepower applications require low torque at high speeds and high torque at low speeds. It is generally accepted that most motors can overspeed by as much as 10% and sometimes even higher. Not all motors are designed to overspeed, so you should speak with your manufacturer to see if your motor is designed for this. VFDs not only vary voltage, but they vary frequency. VFDs vary voltage, they cannot vary voltages higher in which they were designed. In most medium voltage variable frequency drives are capable of outputting frequencies up to 120 hertz. When frequency is increased above 60 hertz, the voltage is not able to be increased above the drive's design, then torque begins to decrease. To keep horsepower constant, if speed increases, then torque must decrease. In other words, variable torque and constant torque applications become constant horsepower applications above rated speed.
High inertia load applications. There are some applications that have inertia problems. Such examples are centrifugal fan or sag/ball mills. Now, the centrifugal fans are variable torque and the mills are constant torque. So the torque profile is not of concern here. But inertia is the resistance of change of a rotating body. Since the rotating body resists change, the motor must work harder and longer to start the load. Larger diameters, heavier weight, and then certain geometries of the equipment equals to a higher inertia. When with direct online or DOL applications, a special motor must be designed to handle the stress of starting or accelerating such a load. VFDs, however, will eliminate the need for special motor designs. Torques. Now there's also starting torques, which is the torque that is required to accelerate the load. The two specifically that we need to be concerned with are lock rotor torque, which is the torque the instant voltage is applied to a motor. And then there's pull-up torque, and there's a minimum value during the start of the motor before it climbs up to breakdown torque. Breakdown torque is the maximum torque a motor can supply running close to its rated speed. The motor torque must always exceed the load torque for a successful start. If you reduce voltage or you reduce the current, it will sacrifice torque. Now, you apply a motor to a VFD, the volts per hertz relationship creates a condition where breakdown torque can be applied throughout the entire speed range, essentially making lock rotor torque and pull-up torques equal to the breakdown torque. Here you see two representations of what we just discussed. The graph on the left shows one location of the lock rotor, or also known as breakaway torque. And then it'll dip down to this minimum location where it begins to pull up, and then it's called the pull-up torque. It'll reach this maximum location of breakdown torque, and as it gets to full speed, it'll operate right here where it's rated at its rating. With the variable frequency drive, this breakdown torque can move throughout the entire speed. So at any time when you're trying to accelerate a load, your motor can put out the maximum torque that it can.
So what Abel is stating there is that throughout the complete speed range of the variable speed drive, we do have maximum torque throughout the whole speed range due to the volts per hertz ratio, which will be explained shortly.
One unit of measurement for motors is the horsepower, and the horsepower is the power measurement required for the motor to produce the required torque. So it is the output of the motor. Horsepower is defined as a torque times the RPM divided by 5252. Now the torque is going to be the full load torque, so whatever is required to move the load. The RPM is the full load speed of the motor, whether it's 3600, 1800, 900, so forth, so on. And then 5252 is a conversion constant in the electrical world. Current. Current is the measurement of electrical energy that is converted by the motor to the rotating energy. So motor converts electrical current to output of horsepower. Now, VFDs protect the motor from going above its rated current or going into an excess overload. VFDs eliminate lock rotor current, also known as inrush current or starting current, which is represented on the right, and I'll discuss that in a minute. Inrush current is a period that a motor encounters 5 to 12 times its rated current. This condition will overheat the rotor, and it is what limits motor starting. However, since the motor never sees such high inrush currents, this condition is eliminated when the motor's on a VFD, and the motors will then have infinite starts. So what this curve represents is when this motor is first starting, it'll see 6 times its rated current. And as it gets up to speed, it'll slowly start to decay till eventually it gets to its rated point, and then it operates right here. If it's a low inertia pump application, this could only be 8 to 12 seconds. If it's a high inertia, a fan or a mill that we discussed earlier, it could be as much as a minute. The entire time, the rotor is getting excessively hot.
Motor control methods and applications: volts per hertz control and vector control. When drives are in volts per hertz mode, they try to maintain a certain volts per hertz ratio. For example, a 4160 volt drive will keep a volts per hertz ratio of 69.33. That is 4160 divided by 60 equals 69.33. When this drive changes frequency, it will also change the output voltage to keep the ratio constant. So if we look at 15 hertz, the drive will output 69.33 times 15 equals 1040 volts. At 30 hertz, the drive will output 69.33 times 30 equals 2080 volts. And at 60 hertz, if we take 69.33 times 60, that will equal 4160 volts. Vector control is somewhat different. Vector control drives manipulate voltage and frequency to produce maximum torque. Due to this, vector drives can produce more starting torque at lower speeds below 1 hertz. There are two types of vector control: open loop and closed loop. Closed loop requires speed sensing device called a resolver or tach feedback on the motor, sending a signal back to the drive indicating motor rotor position. In open loop control, there is no resolver or tach feedback. The drive algorithm simply manipulates the operation. Environmental concerns.
So what are the environmental concerns when you're applying a motor in a VFD? So first of all, you have to look at the hazardous area. Now, if you're looking at specifically a Division 2 or Zone 2 area, or Division 1, Zone 1 as well, but for Division 1 and Zone 2, for Division 2 or Zone 2 areas, special testing is required to confirm all motor components will stay under hazardous area temperature limits. Now, since these areas are considered
Excuse me, Abel,
yes.
Why don't you start the whole slide over? We'll
Okay.
just make a clean break here.
All right.
All right, go ahead.
So what are some environmental concerns when applying a motor in VFD to a hazardous area or to an area? First of all, when you look at hazardous areas, specifically, let's talk about Division 2 or Zone 2 areas. All right, special testing is required to confirm all motor components stay under the hazardous area temperature limits for that given gas or dust. Since those areas are supposed to be built as non-sparking machines, shaft grounding cannot be utilized for shaft currents. Other enclosures that may have problems, now we'll talk about Division 1 or Zone 1, are the totally enclosed explosion-proof motors that are typically not VFD driven because of shaft current potential. However, with special care, a totally enclosed air-to-air cooled, otherwise known as TAC, or totally enclosed water-to-air cooled, otherwise known as TWAC motors, with an inert gas purged into the motor before start, may be utilized in Division 1/Zone 1 environments, can be driven by a VFD. Another concern is the space heaters. Okay, space heaters must always be utilized when the motor is not in operation to prevent premature installation failure. VFDs have the capability to energize space heaters when the motor is idle without having somebody actually go energize the heaters. Motor and drive testing. So motor testing is predefined by IEEE 112, which is the standard test procedure for polyphase induction motors and generators. So a motor, as it's going through its routine test, will go through a no load current, no load power, and speed. They will measure the winding resistance in ohms. They'll go through a high potential test, a lock rotor, and lock rotor current and lock rotor power input, get a visual inspection, and then have a vibration check. Then you can add to that a complete test, which includes the previous 9 tests, plus a temperature rise of winding, bearings, and frames at rated load. And then they'll measure the current, efficiency, power factor, and speed, and torque at 25, 50, 75, 100, and 125% of the rated load of the motor. Top of all of those values, they will still check a lock rotor torque and a breakdown torque.
Motor and drive testing, standard testing of drives. Drives are completely tested to verify all safety functions operate properly. Drive analog inputs, analog outputs are programmed and tested for proper operation. Drive digital inputs and outputs are programmed and tested for proper operation. Drives are full voltage tested, normally into an unloaded motor. Drives are full current tested, normally into a load bank. Load testing of motors and drives. There are a few locations that can test a motor and drive together. So if there are requirements for dynamometer testing and what have you, there are outside companies that do provide facilities for this type of testing. Some driven equipment manufacturers have facilities, normally limited to low horsepower, but most applications can only be tested at the installation site. So after a motor and drive is installed at the site, we are able to, most companies are able to test and check out the equipment on the site. Things to watch out for.
Things to watch out for. First thing is shaft currents. A shaft current is a current created on the shaft by the magnetic fields that are within the motor. Now, where there is current, there is voltage. If this voltage gets high enough, it can dissipate through bearings or the coupling through the frame to ground. If it does that, it will damage whatever it dissipated through. For example, fluted bearings. These little white match marks is where the balls of the bearing actually arced through this bearing race and then ended up going to ground. Once this starts, vibration will begin to pick up and the bearing will fail if it's not caught quickly enough. What can we do to mitigate shaft currents? Well, the first step is insulated bearings. So what the insulated bearings is, it isolates the bearing from the frame. However, do note that it does not actually remove the shaft current, so they'll still be there. Therefore, the driven equipment must somehow also be protected. In low voltage motors, insulating both bearings or both sides of bearings is recommended. However, in the medium voltage world, only insulating the non-drive end is recommended. A second method that could be utilized is utilizing ground brush or rings. What this is a carbon brush or a ring of carbon fiber that makes a direct contact of the shaft to ground. So therefore, this directly removes shaft currents. However, this method does require extra maintenance to change and or clean the brushes or rings. Again, as we spoke before, this is a arcing device, therefore it is not applicable for hazardous locations. The third method, which really is a last resort, is a carrier frequency adjustment. Now, this is mainly for low voltage drives. For medium voltage drives, since the carrier frequency of medium voltage drives does not typically add to shaft currents, they will be set by the manufacturer and they cannot be changed. However, low voltage drives, they can be adjusted from 500 hertz to 16 kilohertz. Again, this is a last resort, and we think that carrier frequency should not be changed unless insulated bearings and or shaft grounding cannot be done. Motor stator insulation. Everybody knows the industry standard of Class F or Class H insulation. However, these are temperature ratings. They have nothing to do with whether they can be on a VFD. The next step is to determine whether they are inverter duty or not. If the motor insulation is considered inverter duty, that means that the motor insulation can take the excess spikes due to pulse width modulation, or otherwise known as PWM. Okay, so however, inverter duty rating pertains to the winding only. Insulated bearings and or shaft grounding may still need to be added. To be inverter duty, the motor manufacturer must advise the speed range in VT and or CT. There are some non-inverter duty motors that are not suitable for EFDs. However, modern VFD technologies allows some VFD manufacturers to filter the drives, quote unquote, clean enough to run these motors as well. How to choose a drive based on motor installation. The most important thing to really look at is to make sure that the VFD selection does not require special cabling or special external filtering that is rated at a higher voltage than the application to filter before the motor. All of that, any filtering should be done internal to the VFD. Additional application considerations for motors and drives.
Desirable features for medium voltage drives include input isolation switch with lockable handle, fused input contactor, pre-charge circuit, soft charging, not only the transformer, but also the DC bus, lightning arresters, and also output line reactors, DVDT filters, or sine wave filters to extend motor lead length. Different types of drive feeders include vacuum circuit breaker, normally good for 10,000 operations before the need of maintenance. Fused vacuum contactor, 250,000 operations before the need of maintenance. And fused load break switch, operations vary per manufacturer. Other means of controlling motors include smooth line transfer. This is syncing and unsyncing feature, which allows a motor to be brought up on a variable speed drive, soft starting the motor, and then through a contactor arrangement, enabling that motor to be transferred from the drive to the line. So as you can see in this diagram, we would bring the first motor up on contactor M2. When we were to sync this motor to the line, the drive would excel, bringing the motor up to 60 hertz. Contactor M3 would then close and contactor M2 open, and now the motor is running across the line. So this could be done then for motor number 2 and motor number 3. So in short, one of the motors can be selected to start on the drive. When required by the process, the drive can be given a synchronized command and accelerate to 60 hertz. Drive control relays will turn on the bypass contactor and then open the drive output contactor. Motors are then on fixed speed power line operation. When motors are to be removed from the power line, they can either be stopped by opening the bypass contactor or brought back from the power line to variable speed control in a reverse process. So as we see here, smooth line transfer and capture, we have one drive and 3 motors. If you envision a compressor or a pumping application, and I'll use a wet well for an example. So you have 3 motors on the perimeter of a wet well, and flow required is less than 60 hertz. So the variable frequency drive will pick up motor number 1 through output contactor M12, and it'll run at a lower speed, less than 60 hertz. Once again, many energy savings can be had by running less than 60 hertz. When flow requirement it becomes greater, motor M1 or motor 1 will be transferred through the line by using contactor M11. Motor number 2 will then be picked up by closing contactor M22 and will be run on variable frequency until the process requires it to be put across the line using contactor M21, and then we'll go pick up motor 3 through contactor M32, and it'll run on variable frequency as to trim the operation. Protecting motors and drives. Overload I²T, there are many types of overload protections for motors. Motor protection relays, medium voltage variable frequency drives. When controlling a motor with a variable frequency drive, there is no need for additional motor protection, as variable frequency drives are designed with overload algorithms to protect the motor. RTD relays, heat is what destroys motor. Thermal devices to monitor the stator and bearings are critical to motor life. This can be achieved by RTDs or thermocouples reading information to protection relays.
There's also another protection for the vibration. Now there's two types of vibration sensors that apply to motors. Both types should feed information to motor protection. There's bracket vibration, which measures the force of the vibration. This will be measured by an accelerometer in inches per second squared, or by a velometer, which is inches per second. This will apply to motors with anti-friction or sleeve bearings. The other protection that's required is shaft displacement, which is actually movement about an axis due to the vibration. This is measured with proximity probes in thousandths of an inch. However, because of construction, this will apply to sleeve bearings only. Then there's current protection, which is differential current transformers. Motors must be leaded with the neutral point for CTs to work. Now, if a motor is on a VFD, CTs are either to be shorted out, or the motor protection must ignore the signal from the CT when the motor is operated on a VFD, because the CTs will read erroneously. But when you're running a motor on a VFD, any surge capacitors and lightning arresters placed between the motor and the drive must be removed. If they are not taken out of circuit, it will cause catastrophic motor or drive failure. So conclusion and summary. There are many benefits of applying a motor to a VFD. Starting challenges such as starting torques and high inertias can be negated. Reducing speeds to meet a load demand saves considerable energy versus mechanically restricting the load. There are some challenges with applying motors with VFDs. However, those challenges can be overcome through design and or a retrofit. Thank you.
Larry and Abel, thank you very much for that presentation. Now it's time for the question and answer portion. Please participate in the live Q&A with your Zoom invite details. These details also can be found in the Additional Resources tab on the left side of your screen.